So here's a boost converter where we've removed the capacitor that was here. I'll explain a little bit better what the purpose of that capacitor was, but it was, in essence, it was there as a filter. But we will analyze this boost converter from first principles, so using Kirchhoff's laws and things like that that we just learned. In the process of doing this, we will make some pretty big simplifying assumptions, but it will help to give us a sense of why this converter works the way it does. If you take another class like a power electronics class, you will get into much greater detail, and you won't necessarily analyze it from first principles. In particular, there's often some sort of tricks done where you're able to basically look at the circuit in steady state and sort of make some assumptions about how the behavior in the on state and the off state are sort of averaged over. You also will get into more detail, the effect of the capacitor here, the effect looking at the actual behavior of a diode, looking at how this switching is done with transistors, looking at sort of the efficiency of the process and all these other sort of details. But what we're going to do right now is just look at the system sort of from a simplified first principles point of view. So initially, we'll assume that the switch is initially closed. When we close that switch, this transistor acts like a perfect switch, and so in essence there's no resistance in this path. And so the current is going to take the path of least resistance. It's going to take this path as opposed to going through the load, and the current will cycle in this loop, increasing the energy stored in the inductor. And so in this state, we want to find the current in that loop, in that inductor, assuming that initially there was no current flowing through the circuit. The way that we do this is first we generate the governing differential equation for that circuit. We can use Kirchhoff's loop law as we learned previously. If I start at this point in the circuit, as I go around the loop in the direction that I've drawn I first come across the supply, which causes an increase in voltage by the amount V supply. And as I continue, I drop voltage across the inductor, where the drop, if you recall, is proportional to the inductance multiplying the time rate of change of current. And then continuing along, I return back to the location where I started, and so that total change in voltage around the loop is equal to 0. So this is the governing equation, very simple equation. I had a bump in voltage across the supply, then I drop across the inductor, and then I'm back to where I started. In order to find I of t, in essence, I just want to solve this differential equation. If you think back to how we've learned how to solve differential equations, the way that we do that is employing the Laplace transform. So we're going to go ahead and take the Laplace transform of this differential equation. When we do that, V supply we'll treat as a constant E voltage. The Laplace transform of a constant, in essence, we treat like a unit step. One way to think about it is that initially, let's say the power supply is turned off at time t equals 0, you flip it on, and so it behaves like a step. So if we do that, the Laplace transform of a constant or a step will just be E over S. Then we'll have the Laplace transform of this quantity the L is a constant, so it just comes out front. We can look up in our table and recall that differentiation in the time domain becomes multiplication by S in the Laplace domain. So this is the Laplace transform of the first term. This is the Laplace transform of the second term, where differentiation becomes multiplication by S. We also have this extra term due to the initial condition. But for this case, we were told to assume that the current was initially 0. So that will drop out. Once we've taken the Laplace transform, the next thing that we would like to do is then to solve for I of S. We will solve the algebraic equation. And so this negative term here, we can add to the right-hand side. To get I of S by itself, we can divide through by S times L. As I do that, you end up with E divided by L, and then 1 divided by S times S. So that gives us an expression for I of S. And then finally, as it's desired for us to find I of t, the last thing to do is then to just take the inverse Laplace transform. E over L is just a constant that comes out front. If we look in our tables again, the inverse Laplace transform of 1 over S squared is t. It's the unit ramp. So that's what I of t is equal to, and we make the presumption that this function begins at time t equals 0. So, presuming that the current starts at 0, when the system is turned on and the switch is initially closed, the current through the inductor, or the current in this loop, will behave according to this equation. This is a simplification in the sense that we're assuming a perfect switch, an idealized switch, and we're neglecting the resistance in this length of wire, but it's a reasonable approximation. Next, we want to look at what happens when the switch is then opened again. So when the switch is opened, the diode is forward biased, and the current flows outside the loop because it can't flow through this middle branch any longer because the switch is open. So what we want to do is we want to find I of t, in this case, in the off state when the switch is open. But now we can't assume that the current is initially 0 because current was already flowing. Initially the switch was closed, current was flowing through here, energy was building up in the inductor, and so when the switch is opened, there was already current flowing in the circuit. So we can't make the same assumption we did in the previous case. The approach that we'll use for finding I of t is basically the same as we did in the on case though. First, we will find the governing equation for this circuit. We start at some point in our circuit as we go across the voltage source. We step up in voltage, V supply. We then drop across the inductor in the same manner that we did previously with a drop equal to L di dt. And then we drop across the load according to Ohm's law, I times R load. Then we're back to where we began, and the total change in voltage around the loop is 0. So this is the governing equation that describes the current flow through this circuit. We want to solve this differential equation to find I of t. Follow the same process. First we take the Laplace transform. This is just a constant, so it becomes E over S. This has the same form it did in the previous case, where the Laplace transform of the time derivative will be S times I of S minus I of 0. And when we take the Laplace transform of this term, R load is just a constant. The Laplace transform of I of t will become I of S. So this is the Laplace transform of that differential equation, where again we can no longer assume that the current is initially 0. The value of this is whatever the current was at the time that the switch was opened. Once we've taken the Laplace transform, the next step that we want to to perform is to solve for I of s. So we've got two terms with I of s. We have this term, and we have this term. This negative sign will become positive if we add R load times I of s to the right hand side. If I distribute this negative L, I'll have negative L times s times I of s. That again becomes positive when I move it to the right hand side. You can then factor out an I of s from those two terms. So you're left with E over S on the left. You're left with L times I of O, where the negative, multiplying a negative, becomes a positive. On the other side, we can factor out the I of S. So I of S multiplies the quantity S times L plus R load. And then to finish solving for I of S, we simply divide through by the quantity S times L plus R load. And that gives us this expression for I of S. Once we have I of S, the last step is then to take the inverse Laplace transform. This term is relatively simple. We have a constant, and then we have a constant times S plus another constant. So this has the basic form of 1 over S plus A if you rearrange it. And so this is something that with a little manipulation we can find directly in our Laplace transform table. This term, depending on how large our Laplace transform table is, we may not be able to find it directly in the table. And so what we need to do is we need to split this into two terms using what we call the partial fraction expansion. In the previous modules, we performed the partial fraction expansion using MATLAB. In this case, we will go ahead and perform it by hand. Looking at this, we basically have two terms in the denominator, just S, a pole of 0, and then we have a non-zero pole. So we have two poles that are distinct and real. And if you think back to the three different cases, think about which case this applies to, case 1, case 2, or case 3. Since this example, rational function has two distinct poles that are real, the coefficients, or the residues, and the numerators will just be simple constants. So here we have two terms in the denominator. We can split them into two different terms, one for the S and one for the quantity SL plus R load. And so at this point what we want to do is, in essence, we want to be able to solve for A and B. And the way that we're going to do that by hand is just doing some algebra. In order to compare these two terms to the term on the left, we need to do the opposite of what we just did. We need to actually find a common denominator. So in order to combine these two, we need them both to have a denominator of S times the quantity SL plus R load, so that we can combine them as such. In order to make this term have the denominator we desire, we need to multiply the top by S and the bottom by S. Multiplying and dividing by S is equivalent to multiplying by 1, which doesn't change the value of this quantity. In order to make this term have the correct denominator, we need to multiply and divide by the quantity SL plus R load. If we do that, then both terms have the same denominator and we can combine them. So what we'll have is A times the quantity SL plus R load plus B times S, giving us this expression. Looking at the expression we have on the left and the expression we have on the right, the denominators are the same and the entire quantities are equal. Therefore, the numerators must also be equal. Looking at this, we in essence have one equation but two unknowns, since we don't know A and we don't know B. So we have E is equal to, if if I distribute the A, plus B times S. But even though it appears that we have one equation and two unknowns, in actuality we actually have two equations, since looking at the left and the right, all of the S terms must be equal and all of the constant terms must be equal. So looking at just the S terms, on the right hand or on the left hand side we have no S terms, so it's as if the coefficient for the S term is 0. On the right hand side we have an S term with a coefficient of A times L and an S term with a coefficient of B. Therefore, on the left, 0 must equal A times L plus B. We can do a similar thing for the constant terms. S to the 0 is equal to 1, and so this can be thought of as our constant terms. On the left, we have a constant term of E. On the right, we have a constant term of A times R load. If we had a higher order numerator with S squared terms or S cubed terms, then we could also match those coefficients on the left and the right hand side. So looking at this expression, we can solve for our first coefficient A, just dividing through by R load. We get that A is equal to E divided by R load. We can then use the first equation to find B, where if we subtract A times L to the other side, we get that B is equal to negative A times L, and then we can substitute this expression for A, and we get that B is equal to negative E times L divided by R load. So that completes the partial fraction expansion. That's how we solve for the coefficients A and B. Once we plug those back into our expression for I of S, we can do the inverse Laplace transform to get I of t. So this is I of t. This is our expression for I of S from the previous slide, where this is A over S, and this is B over SL plus R load, and then this was the final term from the previous slide. Taking the inverse Laplace transform of the first term is relatively simple. This is just a constant over S, so it's like a step. The second term looks similar to an expression of 1 over S plus A, except we need to get rid of this L. So in essence what we need to do is we need to divide through by L in the denominator and the numerator, and by doing that we'll get a denominator of S plus a constant. Same thing with this term. We need to divide through by L in the numerator and divide through by L in the denominator. Doing that, this L cancels out. We have to distribute, so this R load ends up with being divided by L. In the numerator, that L cancels out. Over on this term, this L cancels that L, this L cancels that L, and we again end up with a plus R load divided by L. So again, this is just a constant times a unit step. This is a constant over S plus A, where the inverse Laplace transform of 1 over S plus A, if we recall, is e to the minus AT, where this is what A is equal to. And if you don't remember that property, you can always look back in your Laplace transform table. Here will also be the same sort of form, S plus A, where this is A, so we will get an e to the minus AT. It's just that the constant's different. So performing that inverse Laplace transform, here's our e to the minus AT multiplying a constant. Here's our e to the minus AT multiplying a constant. This is a step, but since we don't consider our function to begin until t equals 0, we can also just write it as a constant starting at t equals 0. So this is the behavior of the current through our circuit or through the inductor once the switch is opened. So when the switch was closed, the current increased linearly. That's what we found 2 slides ago. And then once the switch is opened, it then will behave sort of as a decaying exponential. So there's some constant term, and then there's a decaying exponential where the rate at which it decays depends on the resistance of the load and the amount of inductance. So let's go ahead and look at what the graph of the current through the inductor looks like. So if we recall, when the switch was on, the current increased linearly according to this equation. That's what we found. It increases basically with the slope of E over L. Once the switch is turned off, then the current behaves according to this equation, where this is what the current, on the previous slide this was called I.O., but in essence this is the current at the point at which the switch is opened. So when the switch is closed, the current increases, and then once the switch is opened, the current then behaves according to this equation, where it will decay. At the point that t is equal to Ts, this becomes 0, and e to the 0 is 1. So what we will have is that this term will cancel that term, and the current is just equal to I of T of S, which is what we would expect the current at the instant when the switch was turned. As t goes to infinity, this exponential will decay to 0, and so this whole term will go to 0, and the current will approach E over R load, and it'll behave in essence like this. So when the switch is closed, current increases, and then when the switch is opened, it will decay. This is making the presumption that that we waited until the current was greater than E divided by R load before we flipped the switch. The way that this boost converter works is to continue to switch the switch on and off in order to achieve an output voltage at the level that we desire. So if we continue to do that, we get this sort of behavior. So the switch here is closed, the current flows in the inner loop, causing the energy stored in the inductor to increase. When the switch is opened, this becomes an open circuit, current won't flow that way. The diode is reverse biased, so the current flows out that way. In this graph, we've sort of exaggerated the ripple in the current. In reality, the frequency with which the switching between the on and the off state is done will be much higher. So there will be ripple, but it will be pretty small magnitude ripple. And so this DC to DC converter doesn't exactly achieve a perfect DC output, but it's a DC output within a reasonable approximation. So this graph is the graph of the current through the inductor. Ultimately, what we're trying to do, though, is we're trying to affect the voltage across the load. And so when the switch is on, in essence, the load is disconnected, so no current flows through the load at all. So this is really what the current through the load looks like. When the switch is on, all the current goes through the switch and none of it goes through the load. Obviously, this isn't the sort of behavior that we want. We're trying to achieve a DC voltage at the load. And so the way that that is achieved in reality is with the addition of the capacitor. So the idea is that when the switch is when the switch is on, there is still current flowing through the load, and where that current comes from is from the capacitor. So the capacitor stores charge, stores energy, which is then released when the switch is flipped. And so in reality, we'll get a much smoother looking kind of output. In practice, the DC voltage, the level of boost that's achieved, is affected by, one way to affect it is by changing the frequency. In reality, the way that these are operated is generally the frequency is kept constant, and what's changed is the duty cycle. That is, the percentage of time that the switch is on or the switch is closed as compared to the total period. Using a higher frequency gives us a smoother output, but at the cost of greater efficiency losses. Every time you switch the transistor, there are efficiency losses. And in practice, the output is smoothed by using a capacitor, which acts like a low-pass filter. And so we're sort of just glossing over some of these practical considerations, but if you take a course in power electronics, you will get to understand these elements in much greater detail.